Happening.
Thank you.
Alrighty. All right, so just a brief history of Kitt Peak. It was established in 1958 under a contract from the National Science Foundation and administered by a nonprofit organization called ARA, which is the Association of Universities for Research in Astronomy. Back before 1958, if you wanted to work on a large telescope, if you were like a PhD student or you're an astronomer and you needed data from a telescope, you had to be part of a university or have your own private observatory that you could use to do all of your research. There wasn't like a centralized area where you could apply for time on a telescope. And so recognizing that need and the desire to be one of the leaders in astronomical sciences, the United States decided to create a national observatory. And if you can tell by about the time, does anybody know what else was going on around 1958? Any guesses?
Gold rush.
Korea.
Close. Maybe a little satellite called Sputnik.
Oh, yeah.
Oh, yeah.
And how the National Science Foundation wanted to keep track of those other satellites as well. So that's why the National Observatory was first established. The reason they chose Southern Arizona and Kitt Peak in particular is because we have excellent conditions up on the mountain. Our seeing is actually sub-arc second on average. It is about 0.7 arc seconds. On average, we have 300 days of sunshine here in Southern Arizona. It's a very southern location in the United States. The mountain's not too tall to need oxygen like Mauna Kea. It's very easily accessible from Tucson, as a international airport nearby, as well as trains. We actually have the University of Arizona right next to us, which has the renowned Lunar and Planetary Lab. And we have a steady stream of graduate students to man all of those telescopes throughout the late evening hours. And then we actually are also on the Tohono O'odham Nation, which is one of the largest Indian nations in the United States. And it's one of the only instances where the federal government actually leases back land from one of the indigenous tribes. And as part of the lease agreement that we have with the Tohono O'odham Nation, we also have, it benefits the tribe greatly because if you've ever been to the visitor center, we actually sell their handmade goods. We promote the tribe, and then we also have preferential hiring. So anybody from the tribe that's qualified for a position up there gets the job first. So we give back a lot to the tribe just by being there. We have a really great relationship with them. The observatory has the largest collection of telescopes in the Northern Hemisphere on any mountaintop in the Northern Hemisphere. We're actually tied right now with Cerro Tololo in Chile. We have 22 optical telescopes, 2 radio telescopes, and then the visitor center itself has 4 observatories that are dedicated just for public outreach, that are used for the public and all of our nighttime programs when we have everybody come up. So I'm going to touch on the 3 major telescopes on the mountain and what they're going to be looking at in 2020 going forward, starting with our largest telescope, the Nikolas Mile 4-meter telescope. It is the largest one that we have on the mountain. When it saw first light in 1973, it was actually the 2nd largest telescope in the world. The goal of the 4-meter telescope was to be an all-around telescope for optical observations. It has both a prime and a Cassegrain focus, so it can work at f2.3 or f9 on a 4-meter telescope. And they really wanted to look at the large-scale structures of the universe. Some of the major projects in its history include measuring the rotational speeds of galaxies to determine the distribution of dark matter around nearby galaxies. There's been multiple different spectrographs on it. One of the first CCD cameras was placed on this camera, or on this telescope. And it actually has a twin telescope identical to this one in the Southern Hemisphere at Cerro Tololo called the Blanco telescope. And so that's also sponsored by the National Science Foundation. And so those 2 telescopes have full coverage of both hemispheres, much like the larger Gemini telescopes that are also run by the National Science Foundation. When we have people up at Kitt Peak, we actually get asked quite frequently, you know, your telescopes were built in the 70s, 80s, and 90s, and the largest one you have is a 4-meter, but we're building 40-meter telescopes down in Chile. How do you guys stay relevant and stay on the cutting edge of science? Well, one of the ways we're doing that is with the Dark Energy Spectroscopic Instrument Program, also called DESI. DESI was jointly funded by the U.S. Department of Energy to have a dedicated instrument studying the distribution of dark matter and dark energy throughout the nearby universe. And so what DESI is actually an optical spectrometer that is tasked to understand specifically the effects that dark energy has on the expansion rate of the galaxy throughout the last 11 billion years. It's a very, very special spectrograph because it actually has 5,000 fiber optic cables at the on the instrument that can measure the spectra of 5,000 individual points of light at any one time. And each one of those fibers are controlled by a robot that can reposition the fiber optic cable to exactly where they want to make a measurement while the telescope is slewing in between targets. So in any given night, you can measure up to 60,000 spectra in one clear night. And they actually did this right before we got shut down by COVID. In a 2-night spree, they got 125,000 spectra on different objects in the nearby local group of galaxies. And so this telescope, with those 5,000 spectrographs, it's actually on the top end of the telescope. If there's any astro imagers in the group, it's like a hyperstar where you have the instrument at the very, very top of the telescope. And actually I have a picture of it right up here. So on the left, you can see the instrument gauge on the very, very top of the telescope. That's where the DESI instrument is. And while it's up at that focus, the telescope can operate at f2.7, and it gives DESI an effective field of view of 38 full moons across the night sky. So you can imagine this thing has a huge, huge eye on the sky. Again, it's going to obtain spectral data for tens of millions of galaxies and quasars in about a third of the night sky. And its goal is to construct a 3D map of dark energy and the distribution of galaxies in the nearby universe, but it can actually see up to about 11 billion light years out. So it's an incredible instrument. Up on the top right, you can see one piece of the pie of the fiber optic cables. And then at the bottom right is the actual instrument itself. So one of the reasons that the 4-meter was chosen to run this program was, as you guys can see, the 4-meter telescope is built like a tank. It's huge. It's got these solid iron mounts. It can support a lot of weight. And the DESI instrument weighs a couple of tons. So there's a couple of tons at the very top of the telescope. So you wanted something that was really, really sturdy to be able to handle this instrument. So when commissioning occurred back in the spring of 2009, this was the very first spectral image that was taken, and it was focusing on a portion of the Triangular Galaxy. And what they did was superimpose an image of the entire field so everyone can get an idea of what the telescope can actually see and how this could potentially work as a spectrometer that measures multiple stars and galaxies all at the same time. So this telescope has been a huge, huge undertaking for the National Science Foundation. It spent 10 years in development. They didn't select Kitt Peak to have it until 2016, and then we started our commissioning in the spring and going into the fall of 2019, and then we wrapped up commissioning at the beginning of March in 2020. So as you all know, COVID struck, and Kitt Peak National Observatory was actually shut down officially on March 16th of 2020. So if you remember, I said that March 14th and 15th, we actually got 125,000 spectra. So the scientists on the DESI project could work on a data set while COVID was happening, while we were shut down and everybody was working from home. I'll kind of get to the shutdown a little bit later, but suffice it to say that this has pushed our entire timeline back on how long DESI is going to operate. And when it's actually going to get back to the main scientific endeavor of the instrument. So as it stands right now, we're gradually reopening the mountain starting in September, where we had to bring all the telescopes back online one by one because they had been essentially mothballed safely for 6 months. And so we're bringing all the systems on one by one with a skeleton crew to make sure that everyone was staying safe with COVID. And we're gearing up probably in the next couple of weeks for DSI to go on a recommissioning run to hopefully get back on the sky permanently by March is the goal. And so DSI is going to be a 5-year-long project initially. And it's, again, trying to measure within that time about 35 million galaxies nearby and about 10 million other stars. So going forward, it could be recommissioned for other projects, but it's such a fantastic instrument. I'm pretty positive they'll keep it on the telescope for quite a while. All right, so next up is our second largest telescope, which is the WIN 3.5 meter. Here's a nice picture with the zodiacal light, and you can probably see the Pleiades up in the top and the Andromeda Galaxy over on the right. The 3.5 meter WIN Observatory is the newest research-grade telescope that was built on the mountain. It saw the first light in 1994, and it's part of the WIN Consortium, which stands for Wisconsin, Indiana, Yale, and NOAO, which was the predecessor to the NOIR lab, which is what runs Kitt Peak now. And the N also stands for NASA, which we'll get to in a minute. But WIN, was being one of the more modern observatories, was built with the new method of building primary mirrors, where on the back of it you have all of those honeycomb looking holes in it to make it super light. So even though this telescope is almost as big as the 4 meter, you can see the building itself is only about 4 stories, where the 4 meter is about a 13-story building, and it's much more substantial in size than our 3.5 meter telescope. It's an advanced telescope in that it's on an alt-azimuth platform, and they decided to employ azimuth focus points. So if you can picture a big fork arm mount, it's got instruments on either side with a tertiary mirror in the middle of the telescope that can direct light to either azimuth point, which makes it really easy to have multiple instruments on the telescope at any given point. And this was done to try and maximize the amount of time that we could have on sky, because usually we take a day to switch between the instruments. As such, we can do a lot more science a lot more quickly, and we have several different instrumentations that we can have on the telescope. So the 3.5 meter WIN offers visible, infrared imaging, and spectroscopy. One of the more famous cameras on this, saw a cat. One of the more famous cameras that's on this telescope is called the APOD, which is the 1-degree imager. So for the imagers in the group, if there's any astro imagers in the group, this is a CCD camera that has 4 CCDs built into it. The total resolution is 1 gigapixel at 11/10 of an arc second per pixel. So extremely zoomed in, very, very good sampling, which at Kitt Peak, we can afford to go that small and that zoomed in because we have great seeing conditions. And down on the bottom right, you can see a representation of one of the first light images from that camera. And it's only, it's not even the full sensor array over there on the Whirlpool Galaxy, but much like some of the Hubble instruments where you have multiple CCD sensors, you have those black lines in between them. So you have to move the camera a little bit in between exposures to get a full picture of the image. Also on that instrument is the WORK IR imager that does infrared spectroscopy. We have the Hydra spectrometer, but that might soon be retired or repurposed to another telescope, as we now have the NEWID spectrometer, spelled N-E-I-D, but it's pronounced NEWID, kind of weird. But NEWID actually stands for vision in the Tohono language. So of course, we wanted to pay homage to the nation on which we're operating, but NASA and their acronyms and the government with their acronyms, we fit all the words of that, what the telescope does, into an acronym to work. So it's the NASA National Science Foundation Explore Exoplanet Investigation with Doppler Spectroscopy Imager. So NUID's a lot easier to say. So NUID was jointly developed by NASA and NSF. And it's really exciting because it is the most sensitive spectrograph to date in existence anywhere in the world. This thing is a monster compared to most of the other instruments that are out there. It was purposely built to follow up on observations from the Kepler mission and more recently the TESS mission that are looking for exoplanets outside of our solar system. And we built this spectrograph so sensitive because we want to be able to detect Earth mass planets within the habitable zone. So if you all have ever followed exoplanet research or the Kepler mission, you probably know that Kepler specifically would identify planets by waiting for the planet to get in front of its host star and block out a portion of the light. And when you think about it, it makes sense. We would look at the light curve and you would see a dip in the light curve and you'd be like, okay, there's a planet there. It's pretty easy, right? But what happens when it's not perfectly in line and you can't see the planet? If you have an orbit that goes around perpendicular to your point of view, well, you would never know it was there. So here's a great example of an instance where looking for planets in this method just would not work. So what NUID does is actually look for that measurable wobble that the planet is causing on the star itself, something called radial velocity spectroscopy. And so, believe it or not, every planet that's in a solar system or around a star, the mutual gravity causes the star to wobble around the center point of the system. And that's something that we can measure. And so here is putting it into American terms, the speed of the wobble that the planets in our solar system actually cause on our sun. So Jupiter, being the biggest planet within the solar system, actually causes our sun to wobble at a speed of 29 miles per hour. Not too fast, but it's, when you consider the sun moving around that much, that's actually kind of surprising. But then you can see Earth down there at 0.23 miles per hour. Well, this spectrograph is going to be so sensitive that we will be able to detect a star wobbling at 0.2 miles per hour, which is about the speed of a desert tortoise walking across the desert. Incredible when you think about it, because we can actually do that at a distance of about 40,000 light years. So at a very, very great distance across our own Milky Way, we're able to detect something moving as fast as a turtle. So that's the goal of NUID, is to detect Earth-sized planets, because we want to find those Earth-sized planets in the habitable zone to make good decisions on where to spend our time with future telescopes like the James Webb Space Telescope, and where we're going to look for exoplanet atmospheres and eventually extrasolar life. So we're very, very excited about the NUID instrument. It saw its commissioning in February of 2020. So again, just like all of us, it was affected by COVID, but this was one that was fairly easy to bring back online. And I believe they're starting up observations very, very soon, hopefully within the next couple of months. And again, guys, if you have any questions on any of this, feel free to jump in there on the chat. Just let me know. All right. So next up, we have the caltech 2.1 meter telescope, which is one of the most historical telescopes that are on the mountain. This is one of the first major optical telescopes that was ever built on Kitt Peak. We actually saw first light on this one in 1964. So it's a little bit of an older telescope. It had a lot of major discoveries throughout its lifetime, but some of the more noteworthy discoveries were that this telescope was the first one that detected distant clouds of hydrogen gas in intergalactic space. So the space between galaxies. It was theorized that there would be real faint hydrogen gas out there, and this telescope was the first one to detect that. We were the first telescope to have a direct observation of gravitational lensing that was put forth by Einstein in the theory of relativity. So that, I believe that happened in the early 70s on that telescope, about 40 years after Einstein thought that it would be there. It was also the first observation of a pulsating white dwarf star. And if you've heard of a fairly famous astronomer named Vera Rubin, this was the telescope that she used to help discover dark matter. And I had a great question. If I'm not mistaken, most of these telescopes are managed remotely. Actually, there's only one that's managed remotely on the mountain, and that is this telescope, the Caltech 2.1 meter. A lot of them could be, but if you think about the age of the telescopes, many of them still have analog control systems, including the 4 meter, until it was revamped as part of the new DSI project. And so when Caltech took over this telescope back in 2014, I think, they created a system on it called the Robotic Adaptive Optics Instrument from 2015 to 2018. And so one of the goals, there was multiple goals of this instrument, but one of the main goals was to be able to remotely operate a research-grade telescope and an adaptive optics system to be self-contained and run by a computer without any intervention of the scientists. So it was kind of funny when I was up there working one night, because there's a grad student that was there from Caltech whose job was to make her job irrelevant because she was working on running the computer the entire time and trying to make sure that they didn't need any kind of human intervention, which you guys might actually think this is funny. She was a grad student in astronomy, like working on her PhD. She had never looked through a telescope. So when I was talking to her in the cafeteria at 11 o'clock at night, I actually brought her back to the visitor center to have her look through one of our telescopes, and she loved it, of course. But I couldn't believe that a future astronomer had never actually looked through a telescope. It's crazy. So the Robo-AO system was really cool because it used a laser to create a fake star in the sodium layer of the atmosphere about 10 kilometers up. And it would actually measure the distortion or the scintillation effect from the star, the fake star, and then make micro adjustments to the telescope optical system to make a perfectly corrected image. So the main goal of that was to show that on a very old telescope with very old analog technology, we could modernize all of these scopes by putting an adaptive optic system and achieve great resolutions and make these telescopes relevant. Well, in 2018, at the end of the project, this specific telescope was actually able to achieve resolution comparable to the Hubble Space Telescope. A smaller telescope by 0.2 meters, but on Earth under a lot of atmosphere. And so it's a lot easier to fix this one when it breaks than sending astronauts up to try and fix Hubble. So as you guys probably know, the major telescopes out there nowadays are throwing multiple lasers on these telescopes to be able to more accurately measure the atmospheric distortion. I believe the Giant Magellan telescope actually has 6 lasers all around the sides of it, which is actually really cool. So Caltech is now using their telescope to have a, what is it called? A new SEDM, which is the spectral energy distribution machine. It's a low-res fast spectrometer to be used on follow-up of transient objects and events. So if you think about the TESS mission and how and soon the LSST mission, where we're seeing all these transient events night after night, this telescope is specifically tasked to take spectra very, very quickly. And now, because it's completely automated, it's one of the only telescopes on Kitt Peak that can do it in a rapid response. So there was a couple of questions. Ron mentioned that had an old ST4 being used back in the late 70s as a guide camera. I'm glad you guys were doing that back then, because guiding a telescope the old-fashioned way through the eyepiece must have been crazy. And then John Hyatt asks, was the original primary mirror used or a new adaptive mirror installed? It's a great question, John. So on the Robo-AO system, It was actually the original mirror that was built in the 60s that was used for this. But what they did was actually pass the light beam through a thin polymer that can make adjustments to the polymer every few milliseconds to warp the light beam as it came into the instrument. And that's how they achieved the adaptive optics and the resolution. So great questions. All right, so those are 3 of the 24 professional observatories up there. All of them are doing very, very exciting things. We can't wait for them all to be completely 100% back online. But definitely come back up and see us, and you'll get to learn more about each one of the telescopes that are up there. Now, if you do come up to see us when COVID ends, I wanted to talk to everyone about the Visitor Center programs, which is what I work at as a volunteer on the side. So the Visitor Center was one of the early visitor centers that was established in the United States, a major observatory. And currently it has a visitor center museum and a gift shop that's built in right up next to the telescopes on the top of the mountain. We have daytime guided tours of 3 of the major telescopes that are up there. The McMath-Pierce Solar Telescope, which is currently under construction, and I'll get to that on the next slide. The caltech 2.1 meter that we just talked about, you can get inside and look around, and we have this really nice viewing gallery that talks about the history of the telescope, and you can actually see the you could see the Robo-AO instrument when it was on there, but now you can see the SEDM that's on.